So we've learned two methods so far. Hamilton's method being the first historical solution to our American problem of apportioning seats in the House of Representatives. So that was Hamilton's method. And then that was taken over by Jefferson's method, the second historical solution to our problem. And we discovered that Jefferson's method had a few drawbacks in that it sometimes caused upper quota violations. It'll sometimes give a state more seats than its upper quota, which is a problem. Makes other people mad. And that problem is even worse in that the states that seem to get the extra seats are often larger states. So the method not only gives states too many seats sometimes, but the states that get the extra seats are usually large states. So it's biased towards large populations. So we have two more methods that are trying to overcome the drawbacks, right? So Hamilton's method had all those weird paradoxes. Jefferson's method has upper quota violations. So our next method is Adams' method, proposed by John Quincy Adams. And it's very, very similar to Jefferson's. He has find a suitable divisor D, just like Jefferson. Using D as a divisor, compute each state's modified quota. That is, you take the state population and divide it by D. And then you give each state its upper quota. So Jefferson gave each state its lower quota, rounded them all down. Adams is going to give each state its upper quota, round them all up. So it's almost identical to Jefferson's, except we're going to round up instead of down. The hard part is step one, finding the divisor D. Same flowchart we used for Jefferson's. Start with a D. We start with the standard divisor, where you take the total population and divide by the number of seats. That gives you the standard divisor. So start with standard divisor. Total population divided by number of seats. So that's a good place to start. Then you find all the quotas, divide each state's population by the standard divisor, and get the quotas. So that's step one, find the quotas. Then round them all up. Round them all up. Add the quotas, add the upper quotas together. We call the sum T. If T is equal to the number of seats in Congress, we're done. And if it's not, then you have to say, okay, is T too small or is T too big? If T is too small, make D smaller. If T is too big, make D bigger. So let's do a little example here. This is the same example we've been working with all of our other methods. Parador's Congress. So I already did the standard quotas. So let's just remind ourselves how we did it, though. So you take the total population, 12,500,000. Divided by the number of seats, which is 250. So we do 12,500,000. And divide by 250. So my standard divisor is 50,000 people per seat. That is, each seat in the Congress of Parador is supposed to represent 50,000 people. So you take each state's population and divide it by 50,000. So we do 1.646 million, that's 1,646,000 divided by 50,000. And that's where you get the 32.92. So you do each state's population divided by 50,000. So when you get the standard quotas, this should add up to exactly 250 seats, right? Now, Jefferson's method would have you round these all down, right? Adams' method has you round them all up. No matter what the decimal part is, you round up. So this is going to be 33, 139. That's the upper quota, yep. 3.08 is going to round to 4, right? Even though 0.08 is small, we're rounding everything up. So this is going to be 42, 14, and 20. Now when you add all those up, what do you get? 252. So that's too many, right? Too many seats in Congress. So what should I do to D? Make it bigger. Too many, make it bigger, right? Go to the flow chart. If T is too big, make D bigger.
So you're going to make it like 5,000.
Sure, let's try that. So for next steps, make D bigger. So I left a little blank here for what D you're going to use now. So we could try 50,500. That's a good guess because with Jefferson's method, remember when we were rounding down, it ended up working at 49,500. So try going the other direction. So now you have to take each state's population, these numbers, and divide them, instead of by 50,000, by 50,500. Okay, so I have 1,646,000 divided by 50,500, and I get 32.59. And then 6,936,000 divided by 50,500, 137.35. So 0.154 million, that's 154,000 divided by 50,500, 3.05. $2,091,000 divided by 50,500, 41.4. 685,000 divided by 50,500, 13.56. And one more, 988,000 divided by 50,500, 19.56. It did? Okay, so now I have to round these all up. So I get 33, 138, 4, 42, 14, 20. Yeah, so I only 33 stayed the same. This one I lost one. It went from 139 to 138. All the rest of them stayed the same. So I'm going to be at 251. Still too big, right? Still too many. So I'm going to make D bigger. 51,000. It comes out to 249 or 248. Okay, that's great. So somebody already did 51,000 and they said that it comes out to 248. So that's too small. So we need to make, when you're too small, you need to make D smaller. That's a pretty small jump from 50,500. Maybe 50,700 or, yeah, that sounds good. Let's try that. Let's try 700. 50,700 is going to be my new D here. So these methods can take a little bit of trial and error. You might have to go through a couple of times here. Yep. You got 250 with 51,000? Oh. Okay, let's double check it then. All right, so let's do 1646 32.27. 6936. Is that right?
So now that's not like two. Yes, we have.
41 exactly. $19.37. Okay, so if I round these all up, I get 33. 136 was exact, so I'm not going to add one to it. I'm going to keep it at exact.
Why would you keep it exact though? It's half
Because
rounded up.
there is no rounding necessary. It's an exact number.
So 41 would say the same as well.
Yep. So what's that come out to? We lose 2 here and 1 there, so we lost 3. Yeah, so it's 248. Yep. Yes. Can you read off the quotas for 51, for 57? Yeah. Okay. Okay. So then when I round these all up, I get 33, 137, 4, 42, 14, 20, and that adds up to 250. So perfect. This is our final apportionment. Uh-huh. Right. Ooh, yeah. So if we look at the standard quotas, right? Which one violated the lower quota? B. Right. So if you look at B's standard quota, 138.72, to be fair, that's exactly how many seats they deserve, 138.72. And the only really fair way to round is say they either get 138 or 139. But how many did we give them? 137, right? So we violated the lower quota. So we did a lower quota violation because they got fewer seats than their lower quota. Their lower quota is 138 and their upper quota is 139. So we have a lower quota violation. So it turns out that Adams' method sometimes produces lower quota violations, and even worse, these consistently favor smaller states. Okay. So Jefferson's method produces upper quota violations that consistently favor large states, and Adams' method produces lower quota violations that consistently favor small states.
now there's one that favors both.
Yeah, so now which the one you want just depends on what size state you live in, right? So we can conclude that Adams' method is no better and no worse than Jefferson's, just has a different problem. So after considerable debate, the apportionment bill based on Adams' method never actually passed, and Adams' method was never used to apportion the House of Representatives. Okay, so here's our fourth solution, Webster's method, after Daniel Webster. So really similar to Jefferson's and Adams. Find a suitable divisor D. Using D as the divider, compute the modified quotas. Then you find the final apportionments by rounding the modified quotas conventionally. 0.5 or higher, round up. Lower than 0.5, round down. So we use the same flow chart, the exact same one, right? If T is too small, make D smaller. If T is too big, make D bigger. And I want you to try in your groups, apportion Parador using Webster's method. So I have it written out here what I did. I used 50,100. There are lots of D's that'll work. I saw 50,200, 50,250, and 50,300 all worked. They all give you the same final apportionment of this. 138, 3, 42, 14, 20. Now compare those to the standard quotas. Oh, whoops, I forgot the 33. Compare those to the standard quotas. These are the exact number of seats that each state should get. Are there any quota rules violated here? No. Everyone either has their exact value rounded up or rounded down, right? So 32.92, they should get 32 or 33. They got 33. So everybody's seems fair here. No quota violations. So Webster's method actually turns out to be a really pretty good method. It produces apportionments that are pretty close to standard quotas. It very occasionally will produce a quota violation, but not that often. And it produces both upper and lower quota violations. But they don't show any bias between large and small states. So occasionally you'll get a quota violation, but it's not like large states are always going to get the benefit or small states will always get the benefit. It also suffers from no paradoxes like Hamilton's method. But surprisingly, it was short-lived. Okay, so it's a pretty good method, but didn't last that long. It was replaced after 1931 with the method we currently use, which is called Huntington Hill. So to summarize chapter 4, we learned 4 apportionment methods: Hamilton's, Jefferson's, Adams, and Webster's. Hamilton's method never violates the quota rule, so it's got that going for it, but it has all these weird paradoxes, things that happen where a state's population can get bigger, but it loses a seat. We can increase the number of seats to be given out, but a state loses a seat. And what was the other one? Oh, when you add a state with its fair share, that can affect the apportionment of other states. So it has all these weird paradoxes, and it does tend to favor large states. Now, Jefferson's method never violates the quota rule. Oh, sorry. It doesn't have any paradoxes, but it has upper quota violations, and it favors large states. Adams' method has no paradoxes either, but it has lower quota violations, and it favors small states. And Webster's method does violate the quota rule sometimes, but it doesn't favor large or small states. So we have a result that's analogous to our result in chapter 1, the impossibility theorem. We have another impossibility theorem called Belinsky and Young's impossibility theorem. It says that any apportionment method that does not violate the quota rule will produce paradoxes. And any paradox-free method will violate the quota rule. So you get one or the other. You either have to violate the quota rule or have all these strange paradoxes pop up. So there is no perfect solution to the problem of apportionment, only better solutions than others. Okay, so for your activity in class, I'm going to have you work through some of these problems.